So as just mentioned, my name is Margolin, and today I'm going to be talking about Reef, which is a system for zero-knowledge regex proofs. And today we're going to be talking a lot about private regex matching. And what we mean by that is we want to match a public regex against a private document. So this has a lot of applications, but we're going to start by talking about APAKE. APAKE, or Asymmetric Password Authenticated Key Exchange, is a protocol that allows Patty to register and authenticate to a server without having to share her password with the server. Of course, the downside of APAKE is the server can't guarantee that Patty's password is anything better than 12345. And of course, having strong passwords is really important to prevent account compromise. So we want to prove that Patty has a strong password without the server learning Patty's password. And we're going to do this with a zero-knowledge proof. The server can express the notion of a strong password with a regular expression. Patty can then register with the server using APAKE and attach a proof that her password matches this regex, meaning that it's a strong password. The server can then verify the proof. Because we're doing this in zero knowledge, the server only learns that Patty has a strong password, nothing else. So the question then becomes, how do you express regexes in zero knowledge proofs? And really what this is asking is, how do we express regexes as circuit satisfiability problems? Because in order to construct a zero knowledge proof, we have to express this as some type of circuit. So let's start with the first approach. Here we have a regex, and if you recall all the way back to your intro theory classes, we can take this regex and represent it as a non-deterministic finite automata. We can then take the heart of this automata, its delta function, which tells you how to move from state to state, and write it up as a series of cascading if statements. If I'm in state 0 and I see an A, move to state 1, etc. And what we can do is, starting at the beginning of the document, apply this delta function once to every single character in the document before ultimately checking if we're in an accepting or rejecting state. And you could take this, as written this code, and code it up in Circom or Socrates and compile it to an arithmetic circuit. But there's a couple of problems with this approach. The first is that of regex expressiveness. So the regex on the previous slide, pretty straightforward. But what about a regex like this? This regex contains something called a look-ahead. And what it essentially is saying is that we want a regex that has an A somewhere in the document, doesn't matter where, a B somewhere, again, doesn't matter where, and we need our document to be between 2 and 6 characters long. You can see how this is useful for something like strong passwords, where we want to say, you have to have 3 uppercase, 2 lowercase, a special character, and a number. The problem is, representing this with a finite automata, specifically an NFA, isn't very good. In particular, look-aheads and their counterpart look-behinds, when represented as a non-deterministic finite automata, have a significant state explosion. Our solution, we introduce a new class of finite automata called skipping alternating finite automatas that allow us to represent look-arounds with significantly fewer states. The second problem with the naive approach we talked about is this process of a for loop iterating over every single character in the document. What this means in practice is that we're going to have to unroll this for loop in the circuit, meaning we're going to have to instantiate delta once for every character in the document. The solution? A recursive proof system. Without recursion, we're going to have multiple instantiations of delta in the circuit. With recursion, we only instantiate delta once in the circuit. This means our circuit is smaller, and the verifier only has to check the final step. This is great for memory. But what about if the delta function itself is expensive? And unfortunately, representing the delta function as a series of cascading if statements is really expensive. In particular, it's going to require on the order of size of alphabet times size of automata constraints. Our solution? We replace this series of cascading if statements with a start state, character, end state lookup argument in the circuit. So, if you're kind of keeping track, this naive solution that we talked about earlier requires size of document times size of alphabet times size of automata constraints. This is bad for large documents, large alphabets, and large automata. Reef, on the other hand, requires significantly fewer constraints, moving all of those terms inside of a log. Reef scales well to large documents, large alphabets, and large automata. So I'm going to talk a little bit more about each of those three components of Reef before talking about some additional applications and how we evaluated it. So, like I mentioned, we introduced a new class of automata called skipping alternating finite automata. And these automata have two key features. First, they don't have a state explosion when instantiating lookarounds. This is obviously good for complex regexes. Additionally, SAFAs take the intuition that with zero-knowledge proofs, if you have multiple wildcard states, we don't actually care what those characters are. They're wildcards. They can be anything. They just have to exist. So here we have the regex from earlier and the corresponding SAFA. With SAFAs, we're able to essentially condense this statement of, the document has to be between 2 and 6 characters long into a single transition. This transition from state 0 to state 5. With a regular NFA, this would require 6 transitions, so significantly more. And in practice, we found that SAFAs tend to have 5 orders of magnitude fewer states than their DFA equivalents. The next key component of Reef is its use of lookup arguments. A lookup argument is a way to prove that a series of values are in a table. Reef uses 2 tables. The first is a private table that corresponds to the private document. And in particular, you can think about it as a table with an index column and a character. And essentially what we have here, as with a private table, is just a cryptographic commitment. And this is a way for us to tie characters to indices in the document. The second lookup argument that we use is to represent the SAFA. And you can think of this as a table with a start state, character, and an end state. This is replacing the delta function, those cascading if statements. So what this means is when we want to prove that a transition is a valid one, we prove that we have a certain character at our current location, and then we prove that given that character and given our current state, the state we want to move to exists in the SAFA table. We also have a bunch of optimizations that we implement for lookup arguments that might be of independent interest. These include document projections, which are a way to run lookups over subsets of large tables, and hybrid public-private tables. Unfortunately, I don't have time to talk about them, but you can see the paper for more details. Finally, we use a recursive proof system. So with a recursive proof system, what we do is we produce a single proof pi for a single invocation of the delta function. So you start with a single invocation of delta on the first character, and then when we get to the second character, we produce a new proof, pi1, as well as an additional proof that the previous step verified correctly. We can do this for every character that we need to check in the document. By doing this, we can reduce multiple claims about the characters in the documents down to 1. And our circuit size becomes parameterized by a single invocation of delta, as opposed to all of them. So with Reef, we wanted to make sure that it was very generally useful, so we looked at a wide variety of applications. These include personalized medicine. For example, you might want to prove for genetic testing that you do or do not have a specific genetic mutation. This can be expressed with a regex. So in this case, we're working over large documents, large SAFAs, but a very small alphabet. Another application we considered is safe browsing with oblivious DNS over HTTPS. Oblivious DNS over HTTPS provides privacy to clients on a network, but a network administrator might want to make sure that clients aren't going to sites with malware. With Reef, we're able to essentially provide both the privacy of ODOH as well as the security seen in traditional network administrative settings. In this case, we're working over small documents, small SAFAs, but a medium-sized alphabet, which is ASCII. And then finally, it might be desirable sometimes for journalists to release redacted versions of source emails while allowing the public to confirm via something like DKIM the authenticity of the redacted email. We can create a regex that expresses the public content and express the redactions as wildcards, and allowing people to both have the privacy of protecting sources while still allowing the public to confirm the veracity of journalistic sources. So to evaluate Reef, we looked at a wide variety of questions. Unfortunately, I don't have time to go through them all here, so I'm just going to focus on these 4. Can the Reef support a variety of regexes and document sizes? Is it efficient for the prover? And how does it compare to existing solutions? For the rest, see the paper. So Reef supports more robust regexes with fewer constraints. As of right now, there's about 4 other systems that do something similar to Reef. And not only does Reef support all of the functionality of these previous systems, it also supports lookarounds. The other thing is we do it with fewer constraints. You'll notice that for all of these systems, and particularly the ones closest to Reef, Zombie, ZK-regex, and ZK-email, they all have at minimum size of document times size of automata constraints. With Reef, we're able to move all of that inside of the log with just a small factor in front, alpha, which is the number of lookups you perform. In practice, across all of the applications we looked at, this is very, very small. Additionally, Reef is a more general purpose solution, so we can support a variety of applications. So Reef is more efficient not only in theory, but also in practice. Unfortunately, at the time of publication, there wasn't any publicly available source code for the other projects, so we baseline Reef against 2 solutions. The first is that one we talked about at the beginning, a DFA, a for loop, and a series of cascading if statements. The second baseline we look at is we replace the for loop with a recursive proof system. So you'll notice there's a lot of X's in these first 2 columns. And that's because even with a server with 764 gigs of RAM, the circuits were too big to compile. Reef, on the other hand, is able to compile across all of the applications we talked about earlier on a laptop with 8 gigs of RAM. Additionally, you'll notice that the number of constraints is significantly smaller, in some cases multiple orders of magnitude. And not only is Reef more efficient in terms of number of constraints, it's more efficient in terms of total prover time. So here we have a couple of the applications where we were able to fully compare Reef to the baselines. Reef's prover time is up to 5 orders of magnitude faster than alternate solutions. So we wanted succinct zero-knowledge proofs for a variety of regexes that scale well for large documents. And by using SAFAs to get better expressivity, lookup tables for document commitment and SAFA transitions, and recursion to get smaller circuits, we get Reef, which has support for a variety of applications with fast prover and verifier times and fewer constraints. And I'll open it up to questions.
Great.